Hello, it's What the Doodle here, and in today's session, I'm going to have a look at yet another old article, and it's by Jeff Atwood from Coding Horror. For those who don't actually know Jeff Atwood, I would say he was the OG tech influencer of back then, and most importantly, he's the creator of Stack Overflow. So if you're a software engineer, you absolutely will have come across Stack Overflow at some point in your career. And obviously it's on the decline now and it isn't used as much as now, but pretty much any technical sort of issue or bugs or whatever that you search on the internet, there is a very high chance that the top results will be from Stack Overflow. So anyway, so his name is Jeff Atwood, and he's also has a sort of a law attributed to him, which he has. I believe it was something like along the lines of, if something can be created in JavaScript, it eventually will be created in JavaScript. I think that was one of his many laws that he's quite famous for. But anyway, so this article is from 2006, and it was kind of controversial. And this was sort of preceding kind of an era when there was a massive drive around the world from politicians and government, and it was this kind of this movement about everybody has to code, the whole thing about the digital economy, the idea that everything is moving towards digitization and computerization, and we need to sort of essentially raise the literacy for everyone. And in order to do that, they believed, or this was the belief at the time, that if we increase if we get everybody to code or to program, then we can make people more effective. Of course, I don't know where the status of that is. I think all of that has died down a lot. Anyway, this was controversial. So that's just to set the context around when this this article sort of appeared. And it is kind of controversial. And I mean, essentially the idea that some people, there does seem to be this thing where it's a bit like, and I would say the analogy is a bit like mathematics. I think it's a noble cause to get everybody to learn mathematics, but not everybody can be a mathematician. That is my sort of conclusion, and that's based on things that I've experienced directly, firsthand, when I've tutored a lot of young engineers, and I have noticed it myself. And it seems to tie up with what has been done in the academic world in terms of the research for it, which is that there does seem to be some people who, that's obviously, I should caveat and say that obviously everybody can learn to code, everyone can learn to program and whatnot. Actually, I should make a distinction. I think everybody can learn to code, but not everybody can learn to program. But what I do believe, or what I have seen from my experience, is that some people just seem to be able to sort of naturally pick it up, or they have a far closer affinity, and it feels a lot more natural to them. Whereas I've seen some other students or juniors engineers who really struggle, and it's noticeable. Obviously, there's probably a spectrum, and there are some people sort of midway between that. But yeah, it is quite noticeable. Anyway, so the title of this controversial article from 2006 is separating the programming sheep from the known programming herds. Now, obviously, he's since updated this in 2014 because this particular scientific paper, or this paper, was retracted by the author. And we can actually see this quite important here. It says, or the statement is, in 2006, I wrote an intemperate description of the results of an experiment carried out by Saeed Nadi. I hope, probably pronounced that wrong. Many of the extravagant claims I made were insupportable, and I retract them. I continue to believe, and this is important. So although he's retracted, he's made some sort of wild claims, essentially. Maybe they were a little bit overblown. But he's saying, I continue to believe, however, that Dinadi had uncovered the first evidence of an important phenomena in programming learners. Latest research seems to confirm that belief. So essentially, whilst the claims that he'd made were probably a little bit hyped or overstated, the kernel of it, like the actual kernel of it, he still believes it. So although maybe it's essentially saying that maybe he's been a bit too forceful in the claims, but the actual kernel still remains the same. And that kernel is, I would say, and that is something that I've seen myself as well, which is, as I mentioned right earlier on, is that there does seem to be an affinity with some individuals that find it easier to pick up programming versus other individuals who struggle, and that's not there is something there. I think a lot of people have a lot of people in the professional industry may have noticed that as well. So anyway, let's continue. A bunch of people have linked to this academic paper, which proposes a way to separate programming sheep from the non-programming goats in the computer science classes. So of course, I think this is quite inflammatory in some sense, because obviously it's not nice to compare people to it's almost antagonistic to call people but it's from an expression separating the goat, like the separating the herd kind of thing. There could have been, I think it could have been much more less inflammatory, but I think it was the clickbaity of the day. I think obviously nowadays we have clickbait thumbnails and whatnot, but in those days, well, not I say in those days as if it was a long time ago, it kind of is. I mean, it's 2006, before sort of streaming and all this kind of YouTube stuff was more popularized. Most of the stuff was consumed through blogs and things like that, and blog/articles, whatever you want to call that. So yeah, it's the TLDR of that's it's kind of inflammatory, but it's more because it's more for the clickbait more than anything. So long before the students have ever touched a program or a programming language. And then he goes into a quote: all teachers of programming find that their results display a double hump. It is as if there are two populations: those who can program and those who cannot program, each with its own independent bell curve. Almost all research into programming, teaching, and learning have concentrated on teaching. Change the language, change the application area, use an IDE, and work on motivation. None of it works. And the double hump persists. We have a test which picks out the population that can program before the course begins. We can pick apart the double hump. You probably don't believe this, but you will after you hear the talk. We don't know exactly why it works, but we have some good theories. And then he goes on: I wasn't aware that the dichotomy between programmers and non-programmers was so pronounced at this early stage. Dan Bricklin touched on this topic in his essay, Why Johnny Can't Program, but evidently it's common knowledge amongst those who teach computer science. Despite the enormous changes which have taken place since electronic computing was invented in the 50s, some things remain stubbornly the same. In particular, most people can't learn to program. Between 30 and 60% of every university computer science department's intake fail the first programming course. Experienced teachers are wary but never oblivious of this fact. Bright-eyed beginners who believe that the old ones must have been doing it wrong learn the truth from bitter experience, and so it has been for almost 2 generations, ever since the subject began in the 60s. You may think the test they're proposing to determine programming aptitude is complex, but it is not. Here's a question, verbatim. Read the following statements and tick the box next to the correct answer. Int A is equal to 10, int B equals to 20, and then A equals to B. And then you have to sort of select the answer from here. Now, of course, I'm not going to give it away. Let me just zoom in and you see this kind of these kind of questions on Twitter, and it's I should say X. They appear quite often, like, oh, look at this chunk of code, what's the answer to it, all this kind of stuff. But it's an interesting test. It really is, because obviously obviously as a programmer it's completely obvious what the answer is, but it's interesting that this is the test, or a test like this. I'd call this a very trivial test, can determine right at the onset, when someone who's just starting to learn programming, and this can be almost like the litmus test to see if they are of which hump do they belong in, or I don't want to use the word hump, but which group do they kind of belong in. do they belong in the group that have an affinity towards the ability to learn programming, or the or the affinity to struggle in terms of learning programming? So, and it's saying here that this test seems trivial to professional programmers, and it is. It is. But remember, it's intended for students who have never looked at a line of code in their lives. The other 12 questions are all variation on the same assignment theme. The authors of the paper posit that the primary hurdles in computer science are assignment and sequence, recursion, iteration, and then he goes on to concurrency in that order. Thus, we start by testing the very first hurdle novice programmers will encounter, assignment. The test results divided the students cleanly into 3 groups. 44% of students formed a consistent mental model of how assignment works, even if it was incorrect. 39% of students never formed a consistent model of how assignment works. 8% of students didn't give a damn and left the answers blank. So that's interesting. So that's essentially saying that 44%, so just under a half of that hump, had that affinity. I would say it clicked. That's what I mean. So that's not to obviously say. So the interesting part of it is I don't know. That's not to say, oh, they're permanently in this group. That's the thing. It's just that they struggled with that in order to, and I think that's where that 44% had that advantage, I think, is that they understood it. It's conceptually, I call it in the programming world, or I like to call it something clicking. When something you have a concept, you don't quite get it at first, and then one day it clicks. That's what I think that's what I understand it to be, is that those 44% where programming came naturally to them or very easily, or they had an affinity to it, is because it just clicked with them. But this other group, it didn't, and that's why they obviously struggled later on. Of course, as I just said, it'd be interesting whether, because I don't think that's obviously as a snapshot in time. I don't know over time if it clicks later on, because I think it's possible. I think it's absolutely possible, and obviously every form of teaching and all this kind of stuff, because that's the other thing. Learning curve is an interesting thing, because obviously everybody learns at a different rate, and everybody also learns slightly differently. And I think some of the issues, and this is way broader topic in terms of education, all that kind of stuff, but you can't have a sort of one shoe kind of approach to learning, and then just expect everybody to fit that cookie cutter shape. Because, as I said, everybody has different levels of understanding, different ways of learning, and different learning rates. And so it would be interesting. For me, it's very interesting to understand. Okay, we clearly there is that separation, but how can we help improve? For those, but it is quite a large chunk though. The rest, if you almost 60% don't get that, it doesn't click for them. Number one, what can be done to improve that? What are other ways that can be taught, in order to get that, just for that mental model to click? And also, secondly, does it later on for those? Does it click? And I think there are, what I believe is there are sort of layers and levels, if you like, of mental abstraction and complexity as you go up the chain. And I think what happens is, obviously, this particular assignment and sequence, which is like the very foundation at the bottom, before you can sort of, because each one of these, and it's kind of like these layers, if you like. You have recursion, iteration, concurrency, and then sort of, I think further on you'd have things like, type level programming and all that kind of stuff, and it goes on and on and on, essentially. I think, for example, I think everyone has a sort of a level which they struggle with. I think that's what I believe. So, someone who maybe have an affinity, just because they have an affinity at this level, maybe they'll struggle on the second level, and somebody who clicks on the second level might have an issue on the third level, and so forth and so forth and so forth. It just happens to be that this 60%, if you like, kind of struggle on that first level, if that makes sense, in terms of the mental modeling. But that's not to say, again, that it doesn't click. And the reason I say this is because, for example, initially when I didn't get recursion straight away, for example, that didn't quite click, but then it did. and then eventually, pass through that, and then, you go through a whole load of other different levels, and eventually if you do go down that sort of functional programming route, and you start looking into lambda calculus and all that kind of stuff, and especially if you look into languages like, or lazily evaluated pure functional programming languages like Haskell, which you start to get a whole load of other concepts. And initially, for example, the the infamous monad, and initially, again, that was sort of, in order for that to click, it didn't quite click straight away, and then eventually one day it did click. But it's one of those things that just because a mental model doesn't click straight away doesn't mean it won't ever click. So that I think that's important to mention that, because obviously I can see why this is kind of derogatory and inflammatory, in the sense that it says, oh, here are these two groups, and that's just a snapshot. That's a group in time, and I think at all times, or if you put it on a timeline, we were all in that group that didn't get it, if that makes sense, depending on the level, whatever it is. And it just doesn't have to be. I don't think this just applies to programming. I think it applies to literally everything. So let's carry on. Obviously, this is quite a long article, and I highly suggest you have a look at. I know it's old, but there's quite a lot of gold mine in terms of information on here. So the authors found an extremely high level correlation between success at programming and forming consistent model. Well, that's just stating the obvious in some sense. If you have to have a mental model of the thing that you're working. If you don't have a consistent mental model from the outset, then it's going to be a struggle to understand that particular concept, or to even apply that, let alone. So of course, yes, the success is going to be correlated to an understanding of it. But the question is, how do you get that mental model? How do you build that mental model? And it's not going to be the same for everyone. I think potentially that's where the crux of the issues are. It says, I highly recommend reading for the draft paper, which was remarkably entertaining for what I thought was going to be a dry academic paper. Instead, it reads like a blog entry. It's filled with interesting insights like this one. It has taken some of us time to dare to believe in our own results. It now seems to us, although we are aware that at this point we do not have sufficient data, and so it must remain a speculation, that what distinguishes these three groups in the first test is their different attitude to meaninglessness. From formal logical proofs and therefore programs, formal logical proofs that particular computations are possible expressed in a formal system called a programming language are utterly meaningless. To write a computer program, you have to come to terms with this, to accept that whatever you might want a program to mean, the machine will blindly follow its meaningless rules and come to some meaningless conclusion. In this test, the consistent group showed a pre-acceptance of this fact. I'm not sure. I don't know if I extend it to that. I think it just goes back to mental models. I think they did say something about 8% of students didn't even give a damn and left the answers blank. So 39% full. So yeah, I think it's, again, all of this is just levels of that clicking. Of course, if I suddenly, let's say, if you don't know a thing about a car engine, and I just gave you this question or whatever, you might try and take a stab at it to try and answer it, or you might be like, you'll just shrug your shoulders like, yeah, I don't know. So I think this, I don't know if they're reading too much into this, about this whole idea of pre-acceptance of the fact that these programs are essentially abstractions, and they're like formalized in mathematics and all this kind of stuff. I don't read into it that much. I think the kernel of it is the concept clicking, and for some people that concept is clicked clearly. And I said these concepts are tiered. You have like a lower level, and then it builds upon that, and it builds upon that, and it builds upon that. And each level is more complex in its in terms of like its comprehension, and the other aspect, as I mentioned, yeah. So anyway, so everyone should know how to use a computer, but not everyone needs to be a programmer. Yes, kind of. I do agree, because it's that what I said right at the onset, which is mathematics. It's absolutely, it's very noble that everyone everyone should absolutely learn mathematics, because obviously it touches on so many different areas. but not everybody can be a mathematician. And I think that applies to sort of programming. I think, again, it's good to code, and I think everybody should learn to code, but not everybody can learn to program. And I think that there is a difference. I believe everybody can learn to code. Coding is sort of the mechanical, the sort of putting together, a structure or whatever, writing an expression or something. That's the actual coding part of it. But what differentiates between, well, what I differentiate between coding and programming is actually the ability to express a solution to a computer. That's what I believe, that you can come up, you can essentially implement your solution, or you can express it through this abstraction. That's what that is the difference. It's actually solving problems, useful problems that are useful to the end user, or whoever. Because it's one thing to be able to code, which is just to write some code, and learning a particular syntax or whatever. But it's another thing to take that syntax and then to apply it. It's a bit like everybody can learn mathematics. We all know how to do multiplication. We all know how to do addition. Well, not all. Most of us know how to do all of these things. But there is a stark difference between knowing mathematics and being a mathematician. See, a mathematician, those are the tools. So, like doing calculus and adding and subtractions and all this kind of stuff. Those are the tools. But then the actual solving mathematical problems using those tools, that's when you become a mathematician. And it's the same thing with coding. That's what I mean. So you've got the syntax, which is kind of like the tool, if you like. The actual the various different tools. But it's putting together those tools in order to solve a problem, and that's programming. So that's the key difference. So yeah, that is this article, and I do separating programming sheep from the non-programming goats. I highly suggest that you go have a read of this in detail, and also follow through to each of the papers that are listed here, as well as the other sort of related references to click through it and read that. But in summation, I found it an interesting article because it stuck in my mind even all these years later, because at the time it was pretty controversial, and there's a whole lot of conversation back and forth from it. And some of it from the outset sounded a bit derogatory and inflammatory, and it was, and it did upset a lot of people. And in fact, the very fact that entire papers were retracted and all this kind of stuff. But if you put all that aside, it really is essentially, or I believe, the kernel of it, and it as I mentioned earlier, it's based on things that I've experienced myself firsthand, so I can attest to it, I can vouch for it. And I think that kernel, so if you take all the sort of controversy and put that to one side, at the kernel of it, it just essentially says that not everybody has a particular mental model at that particular level, and so therefore if they don't have that, they're going to struggle. That's all it boils down to. And what people have identified in terms of these grouping is essentially groups of understanding in the mental model. And to tackle that is obviously you have to come up with a different strategy, other than if you try and find a one shoe that fits all strategy in terms of learning. That's not going to work, because people are different. Surprise, surprise. People have different aptitude in terms of their learning, and people have different styles of learning. Some people are more visual, some people are more black and white in terms of textual base or whatever. But as I said, so you have to take all of those things into consideration. And so that's all I wanted to talk about. Yeah, very interesting article, and definitely have a read of it. And that is all for this particular session. Well, until next time, I'll see you on the next one.